Good afternoon, everyone. So this is Advanced Thermodynamics and Combustion course being conducted by IIT Guwahati under the NPTEL program, that is National Program on Technology Enhanced Learning. And this is the 10th live tutorial session of this course. And in these tutorial sessions, we have discussion on the topics that have been covered in the lectures of this week. And in addition to that, we take some problems and we discuss those problems and try to answer those problems. Okay, so for this week, the theme of the lectures is thermodynamics of reactive systems. So we shall have discussion on topics that come under this theme, and we will also take questions based on this theme. Instructor for the course is Professor Niranjan Sahu. He is a professor from Department of Mechanical Engineering, IIT Guwahati. And my name is Aditya Sharma, and I am a teaching assistant for these live tutorial sessions. I'm also from IIT Guwahati, Department of Mechanical Engineering. I'm a research scholar currently uh, pursuing my PhD here. Okay, so let's wait for another few minutes. After that, we will start today's session. Thank you. Okay, so we can start with today's session. So the theme is thermodynamics of reactive systems, right? Uh, this is the third week uh, of discussions on combustion. Okay. Before that, we did all our discussions on uh, thermodynamics, the framework of thermodynamics, right? But here we have come to the application part of the knowledge of thermodynamics that we gained in the previous lectures. Okay, so from week number eight, the theme was combustion and thermochemistry, if I'm correct. Okay, yes. So eighth your week was combustion and on combustion and thermochemistry. So here we were introduced to fundamentals of combustion, stoichiometry, right, and different balances linked to combustion process, energy balance, entropy balance. So this was your week number eight. Then and the first week on combustion discussions, and then the second week on combustion discussions is your week number nine, which is on your chemical kinetics. So here what we see is uh, that okay, we did the discussion on combustion uh, from the surface level. Okay, so it wasn't that detailed. So what we do is in the next week we do a discussion on chemical kinetics, right? Chemical kinetics basically is the science where we try to study the rate of a particular chemical reaction. Okay, so this is your chemical kinetics. So we did a handsome amount of discussion on this chemical kinetics in the last week's discussion, right? So here we saw different types of reactions. Okay, first we saw that uh, the reaction that we see in the form of a reactant and a product and its reactants and its products is not that straightforward. So what is the addition here is that it's not that the reaction takes place in a single step. There are a number of steps involved in it in a single chemical reaction, right? That lead to your final products. So, what are these steps? So, these steps basically are some reactions. Okay, so these are some elementary reactions. So we called these reactions as elementary reactions. So these are some elementary reactions that lead finally to your products. So we saw types of elementary reactions. Okay, so there was unimolecular elementary reaction, then there was bimolecular, then there was termolecular reaction mechanism. Okay, so all this was covered in your previous week's content. There also in the final lecture of this week, we saw different examples. Based on examples, different examples, we try to consolidate our knowledge on the elementary reactions. Okay, as far as the whole reaction is concerned. So this was your week 8 and week 9. Now we are into the week 10, that is thermodynamics of reactive system. So first we did the basic discussion on combustion. We made a base for our combustion discussion. After that, what we did is we moved on to the rate processes. Okay, the study of rates of these chemical reactions. So this was another detail into our analysis of chemical reactions as far as the combustion is concerned. Now the theme is thermodynamics of reactive systems. So this will be a comprehensive analysis of your whole combustion in terms of the thermodynamics, as far as the thermodynamics of a chemical reaction during a combustion. Okay, so let's see the topics that have been covered in this week's content. So these are the topics. There are two lectures in this week's content. First is your lecture 26, okay, and then is your lecture 27. So in lecture 26, what we have done is we have taken, we have tried to understand combustion by means of few reactors. Okay, so four reactors we have discussed in lecture 26. Okay. And these reactors have been discussed in detail. So I'll take these one by one, the topics one by one, briefly, because we have to take questions also, which is the main focus of these tutorials. Okay, so first topic is, oh, wait, change the color. So this is your coupling reaction systems. So what do we mean by coupling here? So as I have already told that we did discussion on chemical kinetics, right? And then when we are trying to understand a system, we try to do it using the conservation, basic conservation laws, right? The conservation of mass comes into picture, right? And then conservation of energy comes into picture. And if your velocity is also involved, so in cases uh, momentum is also involved. Okay, so now we have these conservation equations, and then we have our rate processes, right? The rates at which the different reactions are taking place, or different steps are taking place. So what we do is we couple these uh, two approaches. Okay, so your conservation and your chemical kinetics. They go hand in hand, and this way we analyze our particular reaction. So this is the meaning of coupling here, coupling reaction systems, right? Sorry. So now we have taken four reactive systems to understand this coupling. Okay, and these are your first is your constant pressure fixed mass reactor. Second is your constant volume fixed mass reactor. Third is your well stirred reactor, and fourth is your plug flow reactor. Okay, so these four are there. So first is your constant pressure fixed mass reactor. One good example of a constant pressure fixed mass reactor is your piston cylinder. If the combustion is taking place in a piston cylinder. So this is the boundary of your system. Okay. So this is your constant pressure fixed mass reactor. Okay, so I'll draw these four reactors, and then that will be helpful in discussing this. This is your second, then is your third. Well, so this is your well stirred. Then fourth is your plug flow reactor. So these four types of reactors have been discussed in this lecture. So let's see what the first reactor says. So this is a constant pressure fixed mass reactor. So pressure here will remain constant, okay, and the mass in your system which you are studying will remain constant, right? Yes. Okay. So how do we analyze the system? We analyze system by means of first temperature data. So with respect to time, how the temperature changes. Okay. Then we analyze it using the concentration data. The concentration of different species with respect to time. Sorry. Okay. Then is your volume data. The change in your volume with respect to time. So based on your conservation equations, okay, and your rate equations that we used in the chemical kinetics, that we derived in the chemical kinetics, we try to get the equation for these. Okay, so this way we get the information of how your temperature evolves in the reaction with time, how your species evolve in terms of their concentration, okay, also how your volume evolves. So this way we analyze such system for the from the thermodynamics perspective, okay, comprehensively. So yes, comprehensive is the word. So this is a constant pressure fixed mass reactor. And the equations we get here, so these equations are first order ordinary differential equations, okay. So from the different conservation equations and your equations on chemical kinetics, we get a set of first order ordinary differential equations, and then we try to solve these ordinary differential equations. So we have, so what we have in our hand, we have a set of first order ordinary differential equations. In addition to this, we have values of initial state of the whole system. And based on this data, we solve these equations, and this way we get the whole analysis of our system, combustion system. Okay, so this is your constant pressure fixed mass reactor. Then is your constant volume fixed mass reactor. So here also some things are common if we compare it with the previous reactor. So we are concerned with the temperature that is changing with respect to time. Then we are concerned with the concentration data of different species involved in the reaction that are changing with respect to time. But also here we are concerned with the pressure. Okay, because in such reactors there is change in pressure also. So this way we try to analyze our such system in which combustion is taking place. So the pressure equation and then the concentration equation and then the temperature equations all have been given in your lecture slides. Okay, so moving on to your next reactor type, that is well stirred reactor. So it's a type of reactor in which you have some flow into your control volume or the system that we are concerned with. Okay, so that system we define in terms of some control volume, like this is your control volume. Okay, where we have this is inlet and this is outlet. Okay. First, we assume that the system will remain in steady state. Okay, then we take the flow to be steady. Second, okay, then we also assume that the reactants are perfectly mixed, or the species involved are perfectly mixed. Okay, so this is your well stirred reactor. So here your temperature remains constant, your pressure remains constant, and the concentration of species with. So this is your well stirred reactor. Okay, after that, the next type of reactor is your plug flow reactor. Okay, so this is also a steady state reactor, then steady flow reactor. Okay, also this is one dimensional. Then is that there is no mixing in axial direction. Okay, so no axial mixing takes place in these types of reactors. Also, we assume that the flow is frictionless in this case. Okay, so the process remains same. We get a set of ordinary differential equations and the condition of initial state of the system, the initial values of the different parameters involved in a system when the system is in its initial state. Okay, and then we solve such combustion problem. So this is your plug flow reactor. So this is your inlet and this is your outlet. Okay, so these four types of reactors have been discussed in lecture 26. Then next is your lecture number 27. So all these we have discussed. Okay, so now we will move on to lecture number 27. So here the discussion is on the conservation before and after, conservation of your different parameters or properties before and after the reaction. Not just before and after the reaction, but also when the reaction is taking place, these properties must remain conserved, right? So how the discussion, how these things come out in a chemical reaction during combustion. So this has this is the focus of discussion in this lecture. So let's see these topics. So first is your conservation methods. So when we are trying to study some system, and we are trying to conserve some properties in it. So to simplify the system, what we do is we study that, we assume that the system is one dimensional, and then we try to study such systems. Okay, in terms of their governing equations, be it your mass conservation equation or energy conservation equation. So we do it this way. So there are ways that have been enumerated in the lectures. For example, your first is your steady flow one-dimensional planar geometry. Okay, so we do our study in one dimension only, and in a linear way, right? Then is your steady flow for a one-dimensional spherical geometry, where we study our system radially. Okay, so radially, what are the different parameters, how the different parameters are changing radially. So we try to do restrict our analysis to that. Okay. Then also, if we go one level up, we do our analysis in 2D. Okay, where we understand the system radially also, but also linearly. Okay, so these three have been mentioned in your this topic, conservation methods. Then next topic is your mass conservation and species mass conservation. Okay. So when we are studying or having a discussion on combustion, so first point that is to be noted is your mass must remain conserved, right? And then the mass related to particular species that are present in the reaction. So how we write our conservation equations for the species and for the whole system. So all the discussion has been done here. Okay. So your partial differential equations also have been given in the slides for your overall mass conservation and species mass conservation. So if you see your slide number 5 of lecture number 27, so it has been given there, right? Okay. Then your next topic is multi-component diffusion. So in it, different types of diffusions that may take place, okay, in your system, in your combustion system. All this has been discussed here. And the expressions related to it. So if we have to mathematically define or mathematically include diffusion into our analysis, so how do we do that? So this has been done in this particular topic. So four types of diffusions have been discussed. One is your ordinary diffusion, then is your thermal diffusion, then is your pressure diffusion, then is your force diffusion. So ordinary diffusion is the one where the difference in the concentration of different species leads to your diffusion. Okay, concentration gradient basically. And your thermal diffusion comes from your difference in temperatures of different species. Okay, the same way a pressure diffusion comes from the pressure gradients, and the forced diffusion is from the difference in the body forces of different species. Okay. So these are the four types of diffusions that have been discussed in this topic. So this is a multi-component diffusion. So all factors we are taking into consideration here while we are doing our analysis, thermodynamic analysis of a reactive system. Okay. So same way your momentum and energy conservation. So how we do it. So this has been discussed here. So it says that if your viscous and gravitational body forces are absent in the system, in that case, your momentum equation boils down to just d by dx of p equals to 0, where p is your pressure. Okay. Sorry, which essentially means that your pressure is constant throughout your flow field that you are studying. Then your one-dimensional energy conservation equation has been given in the slides. So this is your discussion on your momentum and energy conservation. After that is conserved scalar. So conserved scalar, as the name suggests, we have some scalar property which is conserved for your whole flow field. Okay. So one such example of your conserved scalar is your mixed fraction. Okay. Mixture fraction, sorry. The fraction of this Sorry, yes, your mixture fraction is a conserved scalar. So there are other properties also that can be conserved as scalar properties as far as your combustion discussion is concerned, and these remain conserved. So mixture fraction basically is the mass of material originating in the fuel stream to the whole mass of the mixture. Okay, so this is your discussion on conserved scalar. Then is your conditions for chemical equilibrium. So what happens in a chemical equilibrium? So you have two functions. Okay, one is your Helmholtz function and then is your Gibbs function. So if an irreversible process is taking place in the form of your chemical reaction, if your volume is constant and temperature is constant, this so if your temperature is constant and pressure is constant and your process is irreversible, in that case your Gibbs function starts decreasing as the process moves forward. Okay, and at the equilibrium state it has a minimum value, this Gibbs function. Same is the case for your Helmholtz function, but there uh, it's not the pressure that remains constant, but the volume remains constant. Okay? So this is the thermodynamic conditions for attaining chemical equilibrium. So this is your whole discussion on lecture number 26 and lecture number 27. Okay. So now we will move on to questions. So first we will see conceptual questions. After that we will see numerical questions. Okay. So first question is on your adiabatic flame temperature topic. Because this topic though has been introduced in week 8, I believe, but then the whole discussion is connected. So this question. So please read this question and try to answer this. So the question asks that whether your adiabatic flame temperature calculation requires the knowledge of rate of chemical processes. So rate of chemical processes is from chemical kinetics. So adiabatic flame temperature is that temperature which will be achieved by your products when they are in adiabatic conditions. So the maximum flame temperature that is achieved by products during when the conditions are adiabatic, that is adiabatic flame temperature. So in the discussion on this adiabatic flame temperature, we have seen that nothing as such is required. So we do not require the rate of chemical reaction to define the adiabatic flame temperature. Okay. Simply, we have done the energy rate balance. We have used the energy rate balance while we were defining the adiabatic flame temperature. And by this means only we are able to define our adiabatic flame temperature. Okay. So in that case, this becomes a false statement. So let's see the next question then. So this question is on coupling reaction systems. Question number 2. And here are the options. We can read this question and see the options and try to see what's the answer to this question. So the question is on your piston cylinder based combustion. Okay. So it says that a piston cylinder based arrangement is a case of dash reactor. And the options given are steady flow, constant volume, fixed mass, steady state. So which of these will be correct? So we have briefly seen the type of reactor that encompasses the piston cylinder. And that reactor is, so even if we see a piston, one thing we know that there is no steady flow here. Okay. Then, so this is not your answer. Then if you see constant volume, that is also not true because piston will move. In that case, volume will change. Next is your fixed mass and then steady state. So in such type of reactors, your temperature with respect to time and your concentration of species involved with respect to time will change. Okay. So in that case, it cannot be steady state reactor. Okay. But the mass inside this reactor remains fixed. Correct? So in that case, option C is correct. Okay. So you see the answer is option C. Okay. Then moving on to the next question. The question is on mass conservation and species mass conservation. So before moving ahead, because it's 1 hour already since we started this session, so we'll take a quick short break of 5 minutes and then we will return back and do our remaining session. Okay, thank you. So this is your question number 3, and this is on mass conservation and species mass conservation. Topic from lecture number 27. So this asks that the difference between the species velocity and bulk velocity is referred as a diffusional velocity. So whether this is a correct statement or not. So this is your correct statement. So this is your species velocity, okay, and then this is your bulk velocity. And then this is your diffusional velocity. This diffusional velocity is used in species mass conservation equation. So this is a true statement. Okay. So moving on to next question. So when we define our species mass conservation equation, we also define the diffusional velocity. Question is on plug flow reactor. Please read the question and try to answer it. Okay, so first of all, how does a plug flow reactor looks like? So this is your plug flow reactor, okay, where you have one inlet, one outlet, one outlet, okay, and then there is one more thing, that is in this type of reactor in comparison to well stirred reactor, there will be no axial mixing of the different species involved in the reaction. Okay, the flow will be one dimensional, it will be steady state flow, correct? So now if you see the options, which is not linked to, so steady state is linked to, so in that case this is not the correct. Steady flow, the flow will be steady in a plug flow reactor. Then is one dimensional, whether it will be one dimensional, yes it will be one dimensional, in that case it is linked to plug flow reactor. Fourth is axial mixing, so this is the correct option because there is no axial mixing in case of plug flow reactors. So there are types of reactors. In some reactors there will be axial flow mixing. In this there is no axial flow mixing. Okay. Then we saw constant pressure and constant volume reactors. Their perfect mixing takes place. Okay. So this is answer to your question number 4, option D. So let's see the next question then. Question number 5. The question is on multi-component diffusion. Please read the question and try to answer this. The question is based on the knowledge of thermal diffusion. So what happens in the thermal diffusion? Okay, so the question asks that, or says that, the thermal diffusion results in heavy molecules diffusing from low temperature to high temperature region. So whether this is a correct statement or not. So thermal diffusion is a type of diffusion out of the four diffusion types that have been introduced to us in the lectures, in which the diffusion takes place by the virtue of the temperature gradient between the two species. Okay, so it says that in thermal diffusion, heavy molecules. So out of the two species, if one is the heavier, so in that case, heavy molecules will diffuse from low to high temperature. So if your heavy molecule is at low temperature and the other species molecules are at high temperature, in that case, and that species is lighter in comparison to the former species. So these heavy molecules will move from the low to high region. So whether this statement is correct or not. This is a incorrect statement because it is the lighter molecules that move from low temperature region to high temperature region. And for heavy molecules, diffusion takes place from high temperature region to low temperature region. But this here statement is written wrongly, so this is a false statement. Now moving on to next question. The question asks about premixed laminar flames. So to analyze these types of flames, the governing equations that are considered keeping in mind what type of geometry. This is the question. So please see this question. Okay, so first option here is your planar geometry analysis. This should have been not planar but planar. Then is your spherical geometry analysis. Then is your axisymmetric geometry analysis, or none of the above. Out of these, your spherical geometry is used for evaporation of fuels. Okay, your axisymmetric is used in your jet flames analysis. And your this planar geometry analysis is used for premixed fluids. This basically is one-dimensional planar geometry analysis. Okay, so option A is the correct option for your premixed laminar flames. Your one-dimensional planar geometry analysis is used. Answer is correct. So let's see the next question. Here is the question on conserved scalar, and it's a true or false type of question. Please see this question. So this question says that in a combustion framework, the absolute enthalpy as a conserved scalar remains conserved when there are no sources of thermal energy. So here, absolute enthalpy has been termed as a conserved scalar. This, and then it states a condition for that, that it takes place in this condition. So whether absolute enthalpy is a conserved scalar, and also whether the condition given for the absolute enthalpy to be conserved is correct? We need to answer this. So please try to answer. So this is a correct statement. Okay. So absolute enthalpy is considered a scalar in your combustion analysis of a particular system. Okay. Absolute enthalpy is considered a scalar and it remains conserved if there is no source of thermal energy in your system. Okay. So this is a correct statement. Okay. Then moving on to next question. So A option is correct. So question number 8 says that the temperature gradient diffusion driven mass diffusion is referred as. So temperature gradient, so this is the should have been just Temperature gradient driven mass diffusion is referred as dash. So four options are given. So what will be the correct answer to this question? Is also referred as this. First, the first option is Ludwig effect. Second option is Soret effect. Third is your Brownian effect, and fourth is your Maxwell effect. So this is a fact-based question. And the answer to this question is option number B. Okay. So Soret effect or thermal diffusion, these are one and the same thing. Moving on to next question. So this is a true or false type of question on knocking in spark ignition engines, that is SI engines. One is your compression engine and one is your spark ignition engine, CI and SI. So whether this statement is correct or not. Please try to answer this. Okay. So what happens in knocking? Knocking SI engines. So you'll understand it by means of a graph. So this is your pressure versus time graph. So ideally, your combustion takes place like this, where this point is the peak of pressure that is derived from the combustion. Okay, but in case of knocking, what happens is some instability in combustion is seen. Okay, and this type of behavior in combustion can be of danger to the vessel in which combustion is taking place. Okay, so this must not take place uh, during combustion, correct? And when the statement says that the knocking and sparking ignition engines is an abnormal combustion condition, in that case, this is a correct statement. Okay, so moving on to then next question. Multiple component diffusion. Which of the following are the dominant modes of diffusion flux in a typical combustion system? Please try to answer this. Which of the given options, which two are the dominant in a typical combustion system? Okay, so out of these, option B is the correct option. Okay, ordinary and thermal diffusion. Ordinary diffusion is the one that is based on the concentration gradients, and thermal diffusion we have discussed a lot. So this is on thermal gradients. So B is your correct answer to this question. Generally, in your combustion systems, the diffusion is seen based on these two, and forced diffusion and pressure diffusion are less significant. Okay, so forced diffusion is based on the body forces, difference in the body force, or the body force gradients. That is the forced diffusion. Gravitational force is a type of body force. Okay. So then, moving on to next question. So conditions for chemical equilibrium. For chemical equilibrium to take place, what should happen to the Helmholtz function or the Gibbs function? So at constant temperature and volume, for reaction to be in chemical equilibrium, they decrease. Helmholtz function decreases and it becomes minimum. In that case, option B is your correct option. Okay. Then the last question of this section, conceptual questions section. So this question is on plug flow reactor and it states that which of the following equations is used to describe the pressure and velocity for frictionless flows. First option is your Euler equation, second is your Lagrange equation, third is your Prandtl equation, fourth is your Leibniz equation. So for frictionless flows, the equation we use to describe the pressure and velocity that is momentum equation. Okay, is your Euler equation. So because in your plug flow reactor we assume that there is no friction involved in the flow, that is why it has branched from this topic. So A option is correct in that case. Then now the last section of the session, numerical questions. So this is the information given for question number 13 to 15. So it is a multi-component system of components hydrogen, nitrogen and oxygen. And then binary diffusivity for pairs have been given, three pairs have been given of the components. Then we need to find out first for species H2. For species S2 we need to find binary diffusion coefficient. So the formula for that is simple. 1 minus mole fraction of H2 so this is it from the given question. This is 0.13, 0.27 divided by 2.1 plus 0.59 divided by 2.6. So this will come out to be 2.447. Okay. Same way, question number 14. For oxygen, we need to find is is sorry. Okay, by mistake I gave the answer, but that is fine. We will calculate. So this comes out to be 1.017. Okay. The last question. 1.017. Here also is. Okay. So let's solve for it. This is your dn2m. Okay, so if we calculate this, it comes out to be 1.171 centimeter square per second. So this was your last question, and this way we have come to the end of this session. Okay, so this was your session number 10 on thermodynamics of reactive systems, where there were two lectures. First lecture was on reactors, where we discussed constant pressure fixed mass reactor. Then we discussed constant volume fixed mass reactor. Then we discussed well stirred reactor. Then we discussed plug flow reactor. Okay, so these were the four reactors. After this, After this discussion on four reactors, we moved on to lecture 27, where there was discussion on conservation of different properties as far as the a combustion system is concerned. Okay, so there we saw conservation based on mass, then species conservation we saw. Okay, and then we discussed multi-component diffusion also, how we handle a multi-component diffusion, because mostly in combustions we do not see a binary component diffusion or two component diffusion. We see more than two component diffusion. So how do we handle that? So this has been taken in this topic, right? And then eventually we saw the concept of conserved scalar, and then what are the conditions that are required for the reaction to be in chemical equilibrium. Okay, there we saw how the Gibbs function or a Helmholtz function behaves in that case. Correct. After that, we did 12 conceptual questions, out of which few were factual also. And after that, we did three numerical questions based on binary diffusion. It was a multi-component system, and we found out the binary diffusivity of each species that was present in that system. Okay, and this way we did our session. And so I thank you for listening to this session. And the next session will be on coming Sunday, and the timing will remain same, that is 3 to 5 p.m. So till then, keep learning and goodbye. Thank you.